So we now want to measure efficiency of programs. And in order to do this, a whole theory has been developed, the theory of complexity. So you might have heard of one of its most important problems, open problems, one of the most important problems in the field and even in mathematics, and it's the question of whether P is equal to NP or P is different of NP, depending on how you want to formulate it. Okay, so let's talk a little bit about complexity. Complexity of a computational problem or an algorithm measure its difficulty. And its difficulty in many different dimensions. You can evaluate this complexity in many different aspects. So for instance, time, memory, the number of comparisons that are needed, the number of steps that the CPU is required to perform, etc. In general, you want to measure efficiency with respect to something that's limiting the execution of your algorithm. So if you have a computer with low memory, you would be concerned with complexity with respect to memory. If you have a slow computer or if your algorithm will be extremely computing intensive, you will measure steps complexity or time complexity to try to improve on your algorithm. Given that you are measuring time or steps or memory, there's still one thing to decide. Are you interested in the performance on average or the performance in the worst case? And both exist. You can measure worst case complexity or average case complexity. Also, are you interested in the current situation at the current size of the data that you're looking at or the current size you're computing things at? Or are you interested in the long run? What will happen in the long run? In other words, are you interested in the asymptotic complexity, which is concerned with the complexity as the size of the input increases? Okay, in general, people tend to be more concerned about asymptotic complexity. The main reason for this, for being concerned mostly with asymptotic complexity, is that you can just wait out certain problems. If your asymptotic complexity is good, then in just a few years, computers will have improved and will be able to deal with much, much bigger problem sizes just because they improve. Okay, so let me give you some examples of algorithms and of one example of algorithm and different questions you can ask relating to complexity. So the algorithm would be an algorithm to sort a deck of cards. So think of a few examples. You could just throw all the cards in front of you and pick the smallest, and then the second smallest, and then third smallest, etc. You could be, let's say, 5 people around the table and you want to sort the deck of cards. So the first thing you'll do is you'll split the deck of cards into 5, distribute that, ask each of them to sort the deck of cards, and then merge back the 5 decks that are already sorted into one global deck that is sorted. So obviously this will be easier to do, merging, if the 5 subdecks are already sorted. There are many different algorithms for sorting cards. Go look online on Wikipedia, for instance, and you'll find many, many examples beautifully illustrated of sorting algorithms. Sorting algorithms are in general very important. So we have an algorithm to sort a deck of cards. Now, what kind of questions can we ask? Well, the first is, how much space is required to perform the algorithm? If my algorithm is to throw the whole deck of cards on the table, well, I need 52 spots to hold the cards. Okay, I need to be able to see the 52 cards at once and pick one at a time. If you are a small child and you have a small hand, then you might be more concerned about how to manipulate cards and how many cards you can manipulate at once. So space becomes more important. You can also ask how much time it will take to sort, how many comparisons you need to do, how many comparisons between cards, how many memory manipulations, so how many moves of cards do you need to do. And for maybe not relevant for an algorithm to sort a deck of cards, but how many additions are required to complete the algorithm, how many multiplications. But the important part here is in the worst case. Okay, so you could ask this, how long will it take me to sort this deck of cards if the deck of cards is originally particularly badly ordered? For some, and this bad depends on the algorithm itself. Now, here is another question. How much time is required to perform the algorithm, the sorting algorithm, on average? So here, you are not assuming that you have a particularly bad deck of cards to start with. You're just assuming that you have 1 out of 52 factorial possible decks, and you aim to look at the best performance on average. So essentially, you're trying to minimize the sum of the application of this sorting algorithms to all the 52 factorial decks. So you can see already that in many cases, the worst case complexity will be easier to compute than the average complexity, because here you have to look at all those 52 factorial decks, while here you just have to figure out which one is the worst case. Finally, I've just asked all those questions for 52 cards, but you can be interested in what happens when this n equals 52 goes to infinity, when you're talking about larger and larger decks of cards. So for instance, instead of cards, let's look at the phone book. You take all the names of people in Zurich, you take the phone book, and you aim to sort all those names of people in Zurich. So hundreds of thousands. How long will it take you? And the performance of an algorithm at the level of 52 cards might be very different from the performance. Well, it will be slower, but it might not scale exactly as you expect from 52 to 100,000 or 200,000. Okay, so there's many questions you can ask about complexity, and in this course we'll focus on the most classic example, or in the next lecture we'll focus on the most classic example, which is the example of worst case asymptotic time complexity.